Good morning and welcome to the second part of this course, this mini course. I know most people in the room as of yesterday, but there are some new faces. So we'll just do a new brief round of introductions just to tell us who you are and what you're doing at the moment. Go ahead.
I'm Nick. I'm a PhD student here at Utrecht, the Mathematical Institute. And I'm working on dynamical systems and Neurobiological.
I'm Nico. I'm a postdoc here with Marjolein Dijkstra. I'm a theoretical physicist working on neuromorphic computing. Yeah.
There.
I'm Meerte. I'm a second year master's student at the Universiteit.
I'm Guado. I'm from the UVA. We're both doing the computational science master. So
Okay.
Yeah, I'm Loes.
Okay. Safe.
I'm Annika, and I'm also doing the applied maths masters.
And I'm a home one, and my research was on like biomechanics. And at the moment I don't have affiliation, but before I worked in VMC. So.
Hi, I'm Leonard. I'm a guest PhD student, and I have a background in communication science, and a bit of computer science and electrical engineering. And I do agent-based modeling, epidemiological modeling, as well as in other contexts.
Okay.
No maths.
Thank you very much. And so I'm Daniele, and I work at the VU. And my main research interests are in, well, I split between mathematical neuroscience and, let's say, dynamical systems and numerical methods. And I think this course is drifting more and more towards numerical aspects because I'm trying to put in at this stage a bit more about my own research interests. And yesterday, in fact, we can even just start with that. Yesterday, we did a sort of very quick overview of a few models that exist in neuroscience. So we went through how single neurons are modeled through biophysical models that describe ion channels, and we describe voltages at the level of one single neuron. And then very quickly, I think that went really too fast, but I was pressed for time. I tried to convince you that putting together millions of these units and hoping that a mean field equation comes up on the other side is almost, and that this mean field equation is easy to treat mathematically is basically hopeless. We now know that. And so what we are doing in mathematical neuroscience, and I would say also in computational neuroscience, this is like an interdisciplinary field in which physicists, mathematicians, and biologists all try to put their 2 cents into discussion. We are we're just picking up the problem from 2 sides. On the one side, there is the microscopic side in which we try to take simple model of neurons, not the full blown models, and not the full models with the bells and whistles, and we try to couple many of them and just simulate them and see what happens. This is a perfectly legitimate route and one that I often take as well myself. And on the other side, we are coming up with models that are more of a heuristic nature, in which we don't try to describe neuronal voltages anymore, but rather we identify a neuron with the rate at which it spikes. And this obviously comes up with some severe assumptions. And in the limit, as the number of neurons goes to infinity, one arrives at these nice looking equations that are the neural field equations. So let me just first discuss what the constitutive elements of these are, just in case. So you can think of D being a cortex, which is generic. I will think of it as a surface in R3, but actually also this can have a thickness in R3. There is no problems with that. There's basically a manifold in R3. And the idea, let's say, if you've never seen something like that before, probably the first thing I would tell you is just think of this as being a sum, and you're getting an artificial neural network basically out. But if you want to try and find more biological significance to this model, you should think that a point X on the cortex is what you're seeing here, and this U is a variable, is a macroscopic variable of activity at position x and time t. And what this this equation tells us, it's something about what's the activity, how the activity at position x and time t changes with time. So now if there is no other neurons in the network, and I'm just, so I obliterate this integral term there, and I'm only considering this part here, what I would observe is just a boring decay of activity. And then now other neurons come into play, and what I do now is I'm collecting, I put from point X in the cortex, I'm collecting inputs from everywhere else in the cortex. This non-locality, it's crucial, and it makes it a very special deal, and these type of models that make them also different from partial differential equations. And so what ingredients do I have here? Well, I have a synaptic kernel. Synaptic kernel in this case tells me how it models how wires or synaptic connections run from position Y to position X in the cortex. These synapses don't come with a sign, yeah? They are there or they're not there, but we have seen yesterday that sometimes these synapses can have the effect of enhance the local activity, in which case you can think of W being positive with a particular couple of X and Y, and we would call them excitatory synapses, or they're negative, and we call them inhibitory synapses. And then what we're doing here is we're just passing the local activity through a nonlinear function. This nonlinear function, you can think of it as being your favorite sigmoidal function, a Hill function, or something that just does nothing for that. It returns 0 or almost 0 until a critical value at which it raises up. And therefore, you know, my rule of thumb says, what does this thing do? It says go to position Y. So you're at point X, and it now says go at position Y in the cortex. Check whether your activity is sufficiently high. If your activity is sufficiently high, then you transmit a signal to position X. The signal is mediated by how big is W in that situation. And that is effectively what this integral term does. Now, let me just make a few important caveats. Nobody that has at heart biological realism can believe these models are true. Okay? These are complete toy models. They're made out of, how can I explain this? They're made out of an underlying assumptions in which synapses are slow compared to the incoming train of spikes that they get. And even then, you need a lot of simplifications when you couple some of these things in a network to obtain these equations. There is a big important but out of this. Well, another way that you can look at that is to say, okay, I mean, this stuff can obviously, well, not obviously, it can be clearly mapped to real data, because we now know that artificial neural networks, provided I give them the right Ws, they will just fit any data pretty much. They are almost a non-model. They're a model for anything, in fact. But the way these things have been built up, they were built up prior to the era of artificial intelligence, was quite the other way around. Physicists, you can look into one of the references I gave you yesterday about the history of these models by Wilson and Cowan in a book that I suggest yesterday. So you can also revisit that story. Physicists started to look at macroscopic models. So Wilson and Cowan mostly were the ones initiating that. And their worry was not to just try to bridge scales from bottom to top, was mostly to try and come up with the general rules. And they came up with neural fields of this type. What do we know today about neural fields? We know that if you simplify the microscopic neurons, so if you stop thinking of neurons as being Hodgkin axis and pairing them together, and perhaps take certain types of integrated fine neurons, you can in fact take a limit. And in that limit, your equations would not be these ones. They will still have some resemblance to these ones. They would have some form of nonlinearity here. They will no longer feature the firing rate function, which is really the fudging function that we have in this case. And it would have similar equations that are still non-local and nonlinear. So what I'm trying to tell you here in this long preamble is those models are probably not the most biologically plausible models that we have if you want to build up a macro to micro description. They have been, however, over the course of the past year, that particular equation, over the course of the past decades, they have been mapped to real data, and you'll see some of them in today's tutorial as well. They are fantastic if you want to understand how patterns are formed. And yesterday, this is what we did. We just explored how patterns are formed. And also, there exist more sophisticated models that are more biologically plausible, for which limits can be taken in an exact way without approximations, and they still have structure that is similar to that. So these other models that I don't, on purpose, I'm not showing at the moment because they're just too complicated, they will have perhaps many populations. There will not be one variable, there'll be many variables. In fact, the firing rate itself, this object itself, is an evolving equation that you can track. So you have a law for that tells you how to move. They will have all a local term that is non-differential. So this means you can think there is no derivatives here. This is a local term. It doesn't contain any derivative. The models that I'm thinking about that are more sophisticated and plausible, they have some form of polynomial nonlinearity local there. They all have a non-local term that looks like that. Perhaps it doesn't have an F. It has a rate equation. Some authors, including myself, pompously call these models new generation field models. But I want to stick with neural fields because from now, for today's talk and also for next week's next talk I'll give, I think on Thursday, I want to view this object as a sort of heat equation, the prototype model on which I want to develop schemes. So what we're going to be doing for the remainder of the course is just look at how to come up with schemes that solve this equation as a prototype, because that's what we're going to be using to derive other schemes, to apply to more complicated setups. So what we're going to do today, you're going to probably see a couple of applications of why numerics is needed for neural fields. Some of them are motivated by examples and experiments as well. I'm going to try to develop a theory for Galerkin collocation schemes. So the basic, what I want you to know is that until 2023, there was no notion of what is a finite element scheme for these problems. So if you're used to how people solve PDEs and how other organs are at the moment being simulated, all of the other organs, mostly, I would say not all, but by the vast majority of them is simulated through PDEs, because the rules that regulate those type of organs are either reaction diffusion processes or their motion and stresses. Yeah, all of these type of processes physically are described as PDEs. And if you want to simulate a heart pulsating, or if you want to simulate like the vessel, the flow in a vessel in the cardiovascular system, you're simulating Navier-Stokes equation, and therefore you are picking up a set of predefined libraries that are finite elements, Galerkin, and all this type of stuff. We didn't have anything of that type for equations of this sort. That was really my motivation for start doing some research in the past couple of years. And then by the end of today, we're going to be coding, simulating a full spiral wave happening on a hexagonal piece of cortex. And if you think a hexagon is too exotic to be, it's to be true, just wait for a second, so I'll show you some real data of how cortices go forward. Yesterday we had, I think, a very good lectures in which I was interrupted many times with all sorts of questions, and I would want this to be kept for today as well. Any questions? I can speak 15 minutes without changing slides. Any questions? Let's not see that, you'll see this later. Okay. So what I'm showing you here is data from I would say one of my favorite papers in the area, which I reference at the end of these slides, in which neurons have been collected. They've been grown on a petri dish, so to speak. So these are effectively cultivated neurons and not in vivo neurons. They are they're put effectively, they're grown and then they're observed work. Yesterday, we have seen examples coming from mostly, how would I say, mostly, I think I showed you electrode arrays coming from epileptic seizures in which there were like waves associated with the onset and offset of the epilepsy. And what they observe here in this situation is another type of wave, which you might have seen before. It's called the rotating wave. So these are real data sets that are picked up from a bunch of neurons. Of course, in here you're seeing the image that is being pixelated. Neurons are spiking at different frequencies. The color coding there tells us something about the relative phase. And I don't know if you see that happening, but there is clearly like a rotating object, activity that is being formed. And this one is what happens if you just show this recording here. I think that's the pixel at which they're showing the phase amplitude there. This is to some extent not surprising, because as in PDEs, as PDEs support spiral waves when you endow them with the right amount of excitability, also we should expect something like that happening from a neural field. And in fact, the authors of these brilliant papers, not only do they lift up experiments in which spiral waves are formed, but they also come up with neural field models that are just a change with respect, a small change with respect to the one you've seen before, in which this stuff is observed. Yesterday, we also saw that, I don't know if I have it here, but probably not. We also saw experiments in which spots of activity were formed locally. I don't know if you remember that, but I should probably draw it. At some point yesterday, we showed and we discussed situations in which in a squarish cortex, because of some stimulus being initially impinged and then removed, localized patterns of activity that were stationary, so these are now steady states, they're different from the spiral waves that you've seen, were formed. And in fact, most of yesterday's lecture was about how can a neural field make this stuff be a steady state out of nowhere and using just its own nonlinearity, so to speak. So what have we seen yesterday? That a steady state, like the one that you're seeing over there, satisfies this equation here. Typically, as I told you, this is a non-trivial equation to solve because you have to somehow approximate this function. You don't have out-of-the-box pen and paper solution to that. And then we started using basically a mechanism, using Turing patterns mechanism. We started to look at, once I have this steady state that we call U of X, how do we decide whether this pattern is stable or not? And it turns out that what we have to do is just to analyze, to solve an eigenvalue problem associated with the linearized operator attached to that. And yesterday, without having too much worry about which function spaces we lived in, because we decided to take a non-rigorous approach, we found out that the linearized operator associated to that is one that multiplies a function by -1. And in here, it retains the kernel, of course, and then this function f gets linearized around the steady state, potentially with its own parameters. Parameters can crop up everywhere in the model, but I decided to put them here yesterday. And then you have the function Vy there. So, what you also have seen yesterday in the tutorial is that once you discretize the problem, unsurprisingly, this problem gets turned into this type of problem in which U now is a vector of a certain dimension n, perhaps n is how many nodes you have in your cortex. And once you discretize this problem, the top problem becomes a problem of this type. U is a vector, M is a matrix, F is a vector function that is a function that takes vectors in Rn and returns a vector in Rn. And now, typically, computing a steady state involves solving a problem of the type 0 equals n of u. So you're looking at, this is a set of simultaneous nonlinear equations. There is a nonlinear function coming up through this. P is a parameter, and once you fix it, you compute one of those or an approximation of that by effectively invoking Newton's method. Yesterday, we haven't done it like that. We have actually, I set it up, the problem yesterday, in such a way in which we were only looking at flat homogeneous states. So we were not looking at an equation in Rn, we were looking at an equation is a single scalar, and I selected the problem in such a way the scalar 0 was a solution. So yesterday you didn't, I know you didn't have to have this step. But now imagine that you are trying to really solve, to find one of those guys over there that is a steady state. Well, you'll have to bite the bullet and just discretize the problem. Can I just ask how many in the room are familiar with the implementation of a Newton's method? All of you are, most of you are. Good. So we'll get to that in a second. I didn't assume that you do, so I think you'll get some rehearsal now. But also imagine that numerically I obtain you as a steady state problem with Newton's method. Then I'm gonna have to discretize this eigenvalue problem now. And the eigenvalue problem, unsurprisingly, feels the linearized, or if you want, the Jacobian matrix associated with this problem. And the Jacobian matrix of this problem has a nice structure. It's the identity here. The matrix M gets retained, and this now is a diagonal matrix that has as elements on the diagonal the first derivative of f evaluated at u. So there is a striking parallel, of course, between these two. So now, what I'm trying to convey is that if you go back and try to redo a classical bifurcation analysis or nonlinear type study for a neural field, the same as you've done yesterday, every time you want to compute a steady state, you have to solve a problem in Rn with n potentially large. And then you have to compute eigenvalues of an n by n matrix. Can I just pause for a second and ask if you have questions about that? Because if you lose this, if I lose you now, there is no hope I'm going to rescue you afterwards. Is this all clear? What questions do you have? Rather than if you have a question. Yes.
Can you explain once more what the big N is?
So what is n? I mean, n is a compound letter that says, well, it's a compound function that takes a vector in Rn and sends it to 0.
Yeah, sure.
So if that was an ODE, it would be u prime equals n of u.
Because it's notation.
Yeah. So it's just only a compound operator for this. And so I have to solve n of u equals 0, and I have to compute the Jacobian, the eigenvalue problem with the Jacobian of u, of n with respect to u. And that is the Jacobian of n with respect to u. Yes.
So D is the Jacobian for you?
Yes.
Okay.
This is my notation to say a derivative of stuff. And in here, I mean, if I were consistent, which I'm not, I should have said d with respect to u of f. And this can serve as, so that the letter can have the connotation of a Jacobian matrix, of a standard derivative, or of a Vrije derivative if you're working in function spaces, but let's not get in there. So it's just a
So D is always some kind
derivative,
of derivative.
exactly. But in this setup, and for most of today's setup, you can think of these as being, since what D operates on is a vector valid function, so here I put a vector and I return a vector, then that D will be the Jacobian. With respect to u, I should have stated, but I as you found out yesterday, I very often don't see the P, I just think that P is fixed. You also had a question.
Yeah, so I guess, is this just the vector valued extension or the higher-dimensional extension of what we did yesterday?
Yes, so yesterday, we started from here, but then I said, oh, I know a special equilibrium. Well, I know a special equilibrium that is flat and equal to 0. So first off, we had a scalar version yesterday, right? I was only searching for a single object, single scalar number. And in particular, I had it equal to 0. Now I'm thinking that you want to try and compute a steady state that has some spatial profile, for which I'm going to have to discretize it, let's say, at n points. And so then, as you will see, once I discretize it, you're going to get to a vector extension of what we did yesterday. Yes. Does that address your question? Doesn't seem so.
That's more confused.
So let's say that what I'm asking you to believe then is that, because this is the subject of today's session, is that if you're searching for a steady state that is flat, you have a single nonlinear equation to solve. I think you're okay with that, yeah? But if I want to approximate a spatial profile steady state, then one way or another, I'm going to have to discretize these at endpoints in ways that I have to explain. And this gets us to a vector version of the problem you had yesterday.
So it's not that the field itself is like vector valued, but this is a way of,
But the field is vector valued.
okay.
I mean, yesterday at some point, I don't know if you did that exercise, but you run a simulation in which you first discretize the neural field as a set of ODEs. And those set of ODEs represented the value of the field at that point. If you put U prime here, that's exactly what you did yesterday. And now I'm saying if I have that discretized version that gave me Rn valued U's, yeah, and I set the first derivative to 0, I'm gonna have a system of linear equations. How many of them? N, as many as nodes I have in the simulation. And we're gonna work on that all day. More questions, no comments? There was a P saying that in all of these, P is fixed. That's what I should have said. Now, before getting into a little bit how to do that, I want to show you a little bit what I have done in the last decade on that. So what you're seeing here is a spaghetti bifurcation diagram in which at some point a Turing bifurcation happened here. So yesterday, first of all, perhaps the most striking thing is that I've abandoned ridiculous one-dimensional brains and I'm starting to move towards spherical brains, which is a big difference, so to speak. So at some point, I could do analysis, pen and paper, of this system. And by this, I mean I have a flat state that is completely blue. And at some point, I see patterns with the same mechanism you studied yesterday for Turing bifurcations, only here. I can only, pen and paper, do something at this level. But then what happened is that out of that Turing bifurcation came out a branch. Yesterday, we even explored that by simulation. We saw a branch emanating with time stepping. And what this code does, it solves stacks of zero problems. So it solves stack of steady states, and there is a way in which you can track the occurrence of these steady states as the parameter h changes. In my case, the parameter occurred as the firing rate threshold, we call it, of h. And so what that this diagram says, it says, oh, out of the flat state, a branch of solution emerged. I can tell you, but you will have to believe me, that the branch of solutions that emerge from here as some form of symmetries, and there is more than one branch that emanates from there. Let's not get ahead of ourselves. Initially, this branch was unstable. That's where the dashed lines are. So it means that my code not only computed the steady state, but also computed the eigenvalue problem, determined that there was an unstable eigenvalue, and then returned a coloring that was dashed, let's say in this case, and then it went on and searched for it. So now there are entire courses, and I would say in my previous life, this is all what I did, is I came up with doing numerical bifurcation analysis and tried to cleverly follow these paths. That is not what we're going to be talking about today. We're going to be talking about how can I ensure that the discretized problem is feasible? Because very quickly, as you will find out, this problem becomes unmanageable if you're not careful in doing it. So in this case, also the kernel that I picked was distance dependent. It's dependent on the inner product between x and y, because this time X and Y are two positions on the sphere. And so I wanted a kernel that depended on the geodesic distance on the sphere. That's why I picked a kernel that was part of my inner product impersonation should be this between between 2 points on the sphere. Basically, I have to take the sine, well, the cosine, I think, of the something dependent on the theta angle between them, and that's why I have an inner product there. And then, let's say on these branches, I predicted that either you would have no pattern or you would have some form of patterns there, and then numerical simulations, which are now in blue, should confirm that. So this is not just to show off, it's also to say that actually if you want to engage yourself with determining states in cortices that are believable and start being large dimensional, one cannot escape the problem of how do I robustly simulate this? How do I discretize this problem? In this case, the cortex is the two-sphere. So let's try to think a moment if you are, as I say, there is a whole technology and courses that tell you how to follow this path, but I don't want to do that. I want to just assume that somebody fixes a point H, it fixes the value of the parameter. My parameter was called P in the other slides. In here, the parameter is H. And our objective is to just find a single point on this curve. What would you have to do then? Well, remember you had that operator, and I'm not even bothering with P anymore because the H is now fixed. And I have to generate from a starting guess a sequence of iterates that hopefully takes me to a point on this curve. In here, I'm plotting the L2 norm of the vector, just because I need that scalar. Is this idea okay with you? Do you have questions about what we're doing? I need to discuss with you how these iterates appear. And what I'm implying here is that on each of these points, I will repeat this type of task. Predict and correct, predict and correct. And this is how this curve is drawn. But now I need to have you on board with the following concept. I'm solving a single point on this curve. I need to solve n of u equals 0, and therefore I'm generating a guess. H is constant, the parameter doesn't change, and I'm just coming from below, just for pictorial reasons. I need to just generate a sequence of points that in Rn that gets me there. Yes.
H is what we call P earlier.
Yes, the parameter P is like, in this case, the firing rate threshold, and that's traditionally in the area is called H. Yeah, H is P, sorry. Yeah. I'm lifting some slides from my papers as well, that's why. More questions? So you told me that you're familiar with Newton's, so let's just perhaps let's rediscover it together. How do I do? What's a pseudocode that I would have to take for doing that? I'm going to guess U naught. Typically, the guess would come from previous. Perhaps I know a solution nearby, and that helps me guessing what is U naught. So here I'm showing a horrible initial guess, let's say. Normally, you are better than that. And then what do you do at each k? Well, if you have to solve the problem n of u equals 0, what you do is you update. I think my best advice is to not look at the first line, but just look at the second line. You update you get your next solution by summing to the previous solution, previous approximation, a vector x. And this vector x is the solution to a linear problem. This looks horrible, but basically this thing here is a matrix, is the Jacobian matrix, evaluated at UK, but it's just a matrix. And this one is just a vector because it's now n evaluated at minus UK. So at each step, what do? You solve a problem. Let's see if I can do that. Yeah. You solve a problem AX equals B, in which A is known and B is known. And then once you have X, you add it to your past iterate to get the next iterate. Once you obtain a point, so now I am bang on the line here, I need to decide whether this is stable or unstable. So what will I do now? I will now compute the eigenvalue of the Jacobian matrix at the solution that I get. So this is, in principle, how you would solve any steady state. In ODEs, if you use any continuation software like Auto, MathCont, anything, and any of the softwares for ODEs that automatically spit out these bifurcation diagrams for you, the template that they use is that, exactly the same. Modulo some changes, tiny changes. What's the big difference that we have in any PDE or even in neural fields is that these problems are huge. Imagine that to doing one iterate, imagine you're now n in the order of several hundred thousands. This is very possible in large-scale simulations. At every iterate of the problem, you're gonna have to solve AX equals B with A in a matrix in the order of the several thousands by several thousands. Once you get one there, you have to find eigenvalue problems. So what we are witnessing is a well-known law in numerical analysis that basically states that people split in two kinds in the world, the one that study linear algebra and the one that use linear algebra. Typically, linear algebra is the bottleneck around which you have really to work. And I'm not going to work with you on linear algebra, but I want to at least make you aware of that. What makes things worse for us, and interesting for me, I must say that what I'm telling you now is literally a little bit what got me into the field, is that for PDEs, when you discretize a PDE, so your n comes from a discretization of a PDE, these matrices happen to be sparse. If you use finite differences or finite elements for a PDE, the technology that we have is all geared around these matrices being large, very large, but also very sparse. And this is how effectively humanity got away with doing simulations, literally. But in this case, we are not there. The matrix you have here, if you go back to the tutorial you had yesterday, I gave you a matrix M. Most of you have loaded it. I don't think you have engaged with just seeing it. But the matrix M I gave you yesterday was a full matrix, was this circular matrix. Yeah? So this makes the problem for me very interesting. Yes?
If our weights decay fast enough, can we bifurcate it and get
You have to stick with me. You're going ahead. For instance, yesterday we studied this problem. We were on a ring. So instead of having S2, we had S. I put there a convolutional structure, and the matrix was full. So the first contribution I did in this field was to just use a well-known trick that is seen in fluid dynamics all over the place, and it's something that you also have used yesterday, pen and paper, when you've done the Fourier transform of the convolution. Remember, in Fourier space, we rediscovered that convolution in Fourier space give us products to say, well, I have a way out of this enormous problem. What was the way that we came up with is to say, I can write down this thing here using Fourier transform in a way that says, take the Fourier transform of W, take the Fourier transform of F of U, and then Fourier transform back to obtain this quantity there. And this may seem a very convoluted way to write something very simple, which it is, in fact, a convoluted way to write something simple. But what is nested in this horrible writing are numerical games. So when I imagine for a second that I have to evaluate this right-hand side in the old way I would evaluate to take this object. I would never have that, and I would have matrix times vector. The matrix is full, so I need order n squared operations to carry out that matrix vector product. Now in here, what I can do, I can use FFTs to compute W. In fact, once I compute an FFT of W, I can put it on a side and read it. I don't even need to read this all the time. I just need to evaluate with an FFT this right-hand side here, multiply in physical space, Fourier transform back, and this is done in order n log n operations. So I now immediately say, instead of evaluating this right-hand side with order n squared operations, I can do that in order n log n. which for large n is a tremendous advantage. I don't know if you've ever tried to plot order n squared and order n log n. For large n, they literally go like that. And this nice little trick carries out also when at the linear operator level. At linear operator, I can just now do the same thing in which instead of taking the Fourier transform of f, I take the Fourier transform of f prime v. And so perhaps my very first contribution to the field, not that you care, but it's important for this tutorial today, was to say, oh, if we really want to try and do neural fields on proper cortices, perhaps we should start looking at schemes that do that and replace Newton with a variant of Newton that exploits matrix vector structures like that. And you can now build up bifurcation diagrams that are super efficient. So these are, so this is now a neural field in which things like that are built up. The number of grid nodes I have are of the order of millions. And these things run on a standard computer in, I wouldn't say a second. To just get the full thing, you need minutes, that you're computing many equilibria and many bifurcation, many eigenvalue problems, so to speak. So what I'm trying to pass here, I want to give, before just going to the board and bore you with some numerical analysis, I want to give you an idea of the fact that there is an inescapable problem here, and it's the fact that we have to deal with non-sparsity. We have to deal with the fact that we have to take either convolutions or non-local terms, and that sometimes there is a hack. So whenever you have a convolutional structure, you can in fact use FFTs. But let's face it, in these type of problems, sorry, I think I should see a few movies starting and know whether they're starting or not. Let's try. In problems of that size, you no longer have convolutions. So this is now computations done by a PhD student that worked with me, Sami Petros in Nottingham, and this one by Oliver Smith, in which you're seeing different variants of neural field equations which can have dynamic variables there. And in here, we use that using convolution because just for, I would say, practical purposes, we wanted to have a convolutional structure. And we could still have it because in a sphere, it's easy to get. But this is a situation where we are moving towards real cortices. So these are cortices are taken from images. And also the kernel is not, it doesn't have a form, it doesn't have a formula for it. We're literally taking kernels from reading. I mean, there are ways to measure which points are connected to which points with how many wires. So there are ways in which you can approximate WXY with data. And over there, there is no way we're going to have any convolutional structure. So what I'm trying to impart here, I'm trying to propose here, is that we have to, well, sometimes we can use these FFT tricks, but ultimately, if you want to move to real geometry and real data, we can't. And we have to literally devise schemes that let us deal with the generic case. And that's what I want to do. I want to give you elements of this for the rest of the tutorial today. Yes.
So the one on top, the left top one, is that just noise or is it?
No, so I don't know if you just see, but it's imperceptibly kind of moving. I don't know.
Mm-hmm.
So just now to clarify what's happening there is that in that situation, we performed a bifurcation analysis of a steady state that looks exactly like you see at the beginning. And that steady state, the scheme that we had to have the proper symmetry so that we could preserve the symmetry of the spheres, etc. At some point, it hit a hot bifurcation. And in fact, what you see is that there is a torsional mode. I don't know if you can see that, in which some of these, there are oscillations induced around this steady state. So the answer is this is not noise, not yet. Until tomorrow, there will be no noise. Until Thursday, there will be no noise. This is just a deterministic system that is reaching a point where oscillations are born, and they are born in a kind of rotating way. And in here, instead, you have steady states that undergo a different type of instability. They go more like a traveling instability. And so there is a different type of instability that instead makes spots move. Any more questions or comments? We can now switch into the board. So what I want to do now is I want to try and give you the gist of how we discretize these systems. And what we're going to do and how much we're going to cover really very much depends on you, on your taste, on your tolerance for functional analysis or numerical analysis. And that's something you'll have to tell me very openly at some point. So I want to try to put on somewhat rigorous footing the following problem. I have a neural field equation that is a steady state. We start with a steady state. And I'll try to keep technicalities at bay. And I'm asking myself, how can I simulate how can I discretize this problem? So after a long trip, which I don't know where it will end, we'll have to arrive at a system of this type. And there will be not a unique way of doing that. In fact, there will be classes of ways of doing that. And I'm going to show you initially, heuristically, how at least, I would say, how one can come up with a scheme without thinking too much, and then I'll try to abstract it. So the idea is that for me, the cortex will be a generic domain for now. And one way in which we can, I think, come up with a scheme, and I hope you agree with me that that is relatively intuitive. One intuitive way to get a scheme is to say, I have a set of control points on this cortex. So what is happening is that you have a set of nodes. I will use X even when we are in 3D. So I have a set of nodes Xi. I have N nodes. They're all in the cortex. Let's not get ahead of ourselves with where do I position these nodes. Let's suppose I have these nodes there. And one way to think is to say, well, I have this equation that is valid everywhere. I will demand that this equation is true exactly at each of the nodes that we get. To say, I'm hoping to pin that equation in any of these nodes. And when I do that, there's something I'm compelled to say, right? In the next hour, you'll see me at some point coming up with very abstract formulation and seemingly clever formulations for that. But actually, this is, when I came up with the FFT, this is actually how I represented these schemes in my head. And I want to put a point there, and this is not a naive way of doing it, it's just a heuristic way of doing it. And it's actually close to how most people represent these type of schemes. So let me do that. There is no time here because I'm steady state at the moment. And in here, this equation was valid for all X in the cortex. In here, this is valid for all I between 1 and N. So this procedure in numerical analysis is called to collocate the equation. What we've done is we have taken this equation and we have demanded it to be correct without approximation at 7 points. Have we made progress? A little bit. We're not quite there. Why are we not there? Because on this side, I can imagine that if I collect all the xi's, I have a vector, perhaps. I don't know if you can visualize that. So this one bodes well for writing 0 equals minus u plus, but I'm left with something to be desired here, because unfortunately, inside this integral, I still have the full function u of y. This step is more important than one would think. So I won't delete it there. It's actually important to keep it there, but it's not quite, it's what we would call an equation in semi-discretized form. And the reason why this is semi, you'll see that later. But now what can I do? I would say, look, in numerics 101, people at some point told me how to take integrals. So if I want to take the integral of a given function, I would typically approximate it with some sum. So I would typically have a set of nodes y to take, and it would be masochistic not to take the same nodes that I have there, right? So perhaps my hope is that I can write this like this. So this would be, I'm now taking values of y in the cortex, and y not taking exactly the same values, the same nodes that I had before, and I'm weighing them by the weights psi of j. Any quadrature rule that you can think of, any approximation of integrals, well, not any, but the ones that I know for sure, they can be written like that. And in case, I don't suspect that you have ever opened a finite element solver for whatever reason, but if you did, the horse, everything revolves around taking integrals of this type. So there are tabulated ways in which we can take integrals. So what do we get now? We get 0 equals minus, now I'm going to use a new letter. I'm going to call it AI plus sum for j going 1 to n of w xi xj psi j f of sum for k going 1 to n. No, I'm going to go this way. F of xj, well, f of aj. That's it. So what has happened under the hood here is that, and this is happening for I. So the underlying assumption here is that use the new letter, you use AI to say that this is my approximation to u at xi. So in going from here to here, I wanted to, this is more than just notation, it's actually an important conceptual step. Between here and here, there was no approximation. Could you retain the same symbol because I'm just evaluating that function. But now, since I'm introducing an approximation to the integrals, I'm forced to use an approximating symbol. So I'm going to call this AI. The premise is that AI will be an approximation for u of xi. In here, I'm evaluating at xj, and in here I add f of u at xj, but f of u at xj is f at aj. Are you okay with this manipulation? Otherwise, there will be issues there afterwards. And I finally call this the matrix with elements mij, and I eventually succeeded in finding what I wanted. Matrix times vector A. Are you okay with this? So the first thing I want to do now is that at this point, it should be clearer why, if we want to take any profile, one possible scheme can be expressed in this form. I'm just saying, well, collocate the equation and take quadrature. Yeah? Any questions on this before things get more complicated? Let's play this. Yes.
Are the size here just like your grid spacing or something like that?
So if you are living in a 1D cortex, and let me put it like that. If you're living in a 1D cortex, and if you are taking evenly spaced points, and if you're using trapezium for quadrature, then all of these weights, these are basically, this is H, as we've seen yesterday, H being the same space. But in general, they're just weights attached to a quadrature. But you can think of them as being tabulated. So you typically pick a quadrature and they will give you the sign. That's what I did yesterday by giving H times n times 1. Let's play this game again, and now this is going to be slightly more articulated. You can tell I normally use iPads to give lectures. I'm not a true mathematician. 0 equals minus u of x plus integral wxy f of uy and dy. Same problem, but we now use another scheme that I'm pretty confident you might have seen in some numerics courses, and if you haven't, you haven't missed much really. You can learn it today. You could say, I want to write down my solution in terms of a series expansion. What do I use here? Let me use K. Of some coefficients, which I'm now going to call alpha k, times phi k of x. So I'm now saying, out of my domain, I can compute some, let's call them modes, so to speak. And just for simplifying our life, we'll take them in such a way that these functions are orthogonal, so that the inner product between them is delta ij. I know I'm going fast, and I'm putting a lot of theory under the carpet for now. And then what I can do is just now plug this thing there until into that equation and stop until the first n modes, instead of taking all the sum. So what will I get now? I say I get k. K equals 1 to n of alpha k by k of x plus integral over d w x y. And now this is where this notation becomes really awful. And you put L going 1 to n of alpha L phi L of x, well, phi L of y now, in dy. Can I ask you how many of you have seen before a Galerkin scheme? Because that's where we're headed. 2? Okay. Don't worry, this is just like, it's something that you can pick up fast now. Let's say if you have heard the word Galerkin before, that's what we're doing, but otherwise you can follow me. Remember, my final objective is to get a set of nonlinear equation in which I need A being scalars. I need n scalars for that. And in here, these n scalars are nested inside these sums, so to speak. In the other scheme, things were pretty quick, right? Because immediately by evaluating at xi, by evaluating at xi, I would immediately have access to scalars. In here, I now decided to put the scalars inside, so I have to find ways to do that. But I will now, what one typically do is that, what one typically does is to employ the inner product. So then what you take is you just take a huge inner product of whatever is your right-hand side with phi I. And this one, because of this property that we just drew, that can be relaxed, but because of this property, that immediately takes out the alphas. So now I would have to take the inner product of this sum, and the inner product will feature inner product of phi k against phi j, and that one will give me minus alpha I. And then in here, I'm left with an inner product, which is another integral over d of W x comma y. No. Inner product, I would have phi I x times integral over d of wxy and of sum of L. So I'm just trying to be provocative now. And I need to be told whether this step is understandable or not. I don't expect it would be, but I need to understand where you are in this. So from here to here, what I've done is I tested the right-hand side against phi I. I've then exploited the fact that in here I have a linear combination, phi k on phi I is delta ik, and that's why the only surviving terms is alpha I. And in here, what I've done is I have taken the inner product of this object against phi I. But taking an inner product means taking an integral of phi I of x versus whatever is left here. That's what I did. Yes?
There's the x missing, right? But
Absolutely.
fine.
Actually, in fact, please do correct me.
Yeah.
Like that. Where are our unknowns? First off, are you okay with this writing? I have an unknown here. And then I have an unknown here. And I'm literally now having a deja vu because I am in a situation where this is now also semi-discretized, yeah? In here I had the unknown I wanted, and then nested inside I had this functional form u of y, and that's pretty much the same, in which I have a scalar here, and then I have this function u of y that contains the variables I want. And how did we get out of the woods last time? We stated, oh, I still have to employ quadrature. I'm not trying to approximate the integrals in any way. So let me try to do that by using this formula twice for both the integrals in x and in y. I'll do that. So I'm gonna get, I should say that none of what I will write will be reflected into the tutorial. Right? So you can just be, okay, the tutorial doesn't want you to do any of that. I'm just explaining to you some theory. So now I need an index for the nodes here. Let me use curly L. Phi I of XL. Then I have another sum. Let me use R going 1 to N. W XL XR. And then I still have the F evaluated at, oh, I've used curly L already, so I'm going to use K now. K goes 1 to N, alpha K, phi K, Y is XR. And then both of my weights, the weights in X and the weights in Y. And this maybe doesn't look like a cute thing to do, but this is an equation that you can put in the form 0 equals minus a plus n of a, provided you realize that, just don't write this yet, perhaps you've made an approximation in going from here to here, right? Because we introduced the approximation of the integral. And so these are my a I, and these ones are my a I, ak. So this is now, I wouldn't say that this is a cute system to work with, but it's just another way of writing n of u equals 0. You have like you can write all of these things. This is I going 1 to n. You can legitimately write the collection of this thing as 0 equals some nonlinear function of A. Because you have now all the elements in place for doing that. I can't imagine, yeah.
So why again would you change the alpha I to big A?
AI. So did you, can I ask you, so this is a bad habit that I'm just returning the question to you. From here to here, did you accept this step?
Yeah, well, so thing I'm thinking about is you want to approximate your integral by a finite sum.
Mm-hmm.
So would the best way to approximate it not just be take the first n alpha terms? Or are you saying you take different a's than alphas?
No, I'm just reasoning much more, I think much more pedantically than you perhaps. And I say, this is now an equation that holds for any xi.
Mhm.
And this is the function that I want, and this is the same function that I want. Now I am replacing this equation by another equation, another set of equations. So I can't use the same symbol. So this equation ties the values of u, that is the true solution, to the values of u at its point. But I'm changing the equation, so I'm going to call it AI here and AJ there.
Yeah.
And by the same, I know we do that with that approximation, of course.
So,
and by the same token, I've done this here, because in here, every integral has become a sum. So I'm going to have to switch notation. The alphas have now become A. But but what you're saying, your intuition is correct. You just in here, this is not. I'm not doing any expansion with Galerkin here. I'm just taking finite sums. You can think of ring sums if you like.
yeah, that was my intuition.
Yeah. Except that in numerical analysis, the way you choose xj and xij is you try to minimize the error. So typically there is a theory that says, oh, what's the error that I make? And these error scales with n with a certain power, and that's how you pick up the xi. So it's a different procedure with respect to the ones that you sent your you could even have a different set of n's here. More questions? Yes.
What's the difference between them, like
These
the
two, yeah.
advantage, disadvantages?
Okay, I can immediately tell you one visit. This is horrible to program, right? That's just this is not nice. This Galerkin scheme seems much more complicated to program than this one, let's say.
It must have an
It must have it has advantages and disadvantages. So let's say that Galerkin schemes are so for theoretical reason, it's much easier in actual finite elements codes, yeah, the ones for PDEs, to reason in terms of Galerkin scheme than it is to collocation. I think that I don't know how to say this without saying anything too wrong that I cannot be. So the truth is that you should look at them as being two families of schemes. If you take one root, typically, and that's the collocation root in PDEs, you typically are aiming to have small n's that have very, very fast convergence properties. So typically, you're going through something that are called spectral elements, spectral schemes. And so that means with a small n, you can achieve some form of fast convergence. These schemes, the Galerkin schemes, are typically employed in situations where you have geometries that are more interesting. So you don't have regular geometries like tori, like I've shown you so far. And so that is typically when Galerkin schemes are more preferred. But this has to be vague because just look at them as being two family of schemes, and typically which you pick, it's really a bit picking your poison, really. They both have, I will try to highlight more of them, more advantages and disadvantages. Any more comments? Yes.
Because I study mechanics, we use a lot of finite element.
Yes.
And so.
They look like that.
Yeah, what I did my bachelor, I did it, but now because, but it's like for especially for like for analysis structures, course, structures and for example, the house, the bridge, it's all have complicated geometry. So
Yes.
they can
Yeah.
either have a mesh.
And that's typically the method of choice in this case. Yeah. That's correct. That's an observation I also sympathize with. Okay. So now let me just jump to the conclusion that I have. Well, let me just revisit with you what happens if you have a time-dependent problem. Now I can go super fast. That's the time-dependent version of the problem that you have. And we have two heuristic ways of doing it. You evaluate at xi. You see I've now reinstated the time-dependent term. You then approximate the integral and you arrive at that set of equations. And when I started this 2 years ago, people that would try to do error analysis, there were few and far between, and they were looking at approximation. They would just compare the errors made by this scheme to the true solution. That's what you would do in numerical analysis and say, as n goes to infinity, how fast do I get to 0? Then we've seen another scheme that doesn't try to have point. The second scheme, what it will do is it will say, I have a set of modes, and I have to truncate that. I may use different notation now. You truncate and plug in, you arrive at an equation of this type. This is what we have seen before, and this one is now what happens when you plug in the same answers in the temporal derivative and don't necessarily invoke orthogonality or normality. And then you approximate the integral and you get to a set of ODEs. And for this, there was no time error, no error analysis at all whatsoever. And this hurts. It hurts because precisely in a situation where I want to couple this problem to multiphysics, so I would like to couple these to mechanics version of the brains. I would like to couple neural fields with reaction diffusion equation for diffusions inside fibers. For that, I need to be able to plug into existing finite element software that speaks very much this language rather than that language. Okay, so what's the gist of it? The gist of it is that two things. Then I think I will ask you a question, basically. There's two things that can happen. There's two important messages that I will state now, and then I will get back to it in the next lecture if we don't have time to go through it now. First, if you look at these problems, these two schemes with the right lenses, if you have the right framework, these are the same scheme, which is quite a bold statement. But once you look at it properly, this abstractly comes up with a single scheme. The second, and this was something that I found really surprising a year ago, but now it's kind of very natural for me, is that you can pose the question, what error do I make? Not at this level, but at this level. So let me just try to explain this on this simple semi-discretized problem. So for a moment, wear the hat of a numerical analyst. What you have is you have a true solution u of x, and you are interested in how far you are from this solution to your approximation. So if I do it at this level, I'm going to have to compare uxi minus ai. Okay? For some I. But when I am here, I have done two sorts of steps. One step was to collocate the equation. This may carry an error itself, and in fact, it will typically carry an error itself. What error does it carry? Well, in the limit n going to infinity, I'm going to have knowledge of all the function, yeah? So there will be an error also just by the fact that I'm considering n such equations. And in addition to this, I'm summing the quadrature error, the error that I make by discretizing the integral. So if I look at things at this stage, I'm catching error down the path. If I manage to catch error here, this has tremendous advantages for the analysis. The first advantage is that I can use this this idea that both schemes really look alike once I properly set them. The second thing is that I get an error of a better quality. And this is something that I don't know how much I'll manage to convey, because this depends on how much you care about numerical analysis. There is these are hierarchical processes. If I manage to say what error I should expect before I approximate the integral, I have an advantage that is enormous. If, for instance, I say that by comparing these two objects, I expect an error of the order n cubed, this estimate then will tell me how to choose the integral. Because if I then choose an integral that does not respect order n cubed, I am wasting the ability of the top scheme. And conversely, if I'm now choosing a very accurate Pareto scheme that gives me n to the fifth, I'm still wasting resources because I'm trying to outperform it. The order n cubed cannot be rescued, so to speak. So there is a tension. There is a tension in me, but certainly also in the field, to just try to catch error as early up as possible. And I have been in the camp of not minding for a good 8 years before just realizing this. How is that statement going? Do you appreciate this statement? Okay. So basically, I want you to, the take-home messages before I ask you the question I have to ask is the following. First, there is a way to unify those schemes. Let me show you only the face of it. I'm not going to try to describe this initially. So there is a sense in which the top equation can be written as 0 equals minus u plus wf of u. And this, you have seen it so far in a situation where u is a vector in Rn. But actually, there is a sense in which one can write this where u is a function in the set of continuous functions. So what I'm trying to say is that the neural field problem, once you write it with the right operators, you can turn it into something that returns functions. So this is an operator that takes a function and it returns a continuous function. This is an operator that takes a function and returns the integral of that function against w. And this is the function itself. You don't need to fully appreciate this for the time being, just live with the fact that there is a way to write down the neural field like it looks like a matrix vector multiplied, but it effectively is a functional form of that. This thing, it's typically calling a residual of u. Because it says, I'm trying a u, and I have to make the residual go to 0 for me to say I have a solution. It's called a residual because the moment you perturb u with an approximation of u, this residual is no longer 0. And there is a sense in which I can write the second equation. So this is equation 1, and this is equation 2. And this is the new version of equation 1. And this is the new version of equation 2. In which I have to tell you what is un. Un in that incarnation will be a sum of uxj times some special functions by j for j going 1 to n. So what you do with the collocation scheme here is you stipulate that your solution can be approximated by the value that it gets at all the points times some special interpolating function, phi j. These phi j are not the phi j you saw before. They're just functions that guarantee the interpolation. These numbers are the value of the function there. This is the same procedure. I don't know if I'm resurrecting some numerical analysis or nightmares, depending on how you approach these things. When you try to approximate the original function u of x by a new function that agrees with the function at selected points, you have made an approximation un of x that agrees with the function at selected points. That's called an interpolation process. That's exactly what we're doing here. And you can write down this problem in this form, in which this is a projector operator. We don't have to care about that for now. And the idea is that U does not live anymore in CD, it lives in a subset of CD, it lives in the span of these functions. When I do these type of things, this Pn is just a projector that perhaps you don't care, we will not care about, but I need to stipulate it here. Now I have two different functions, and I can ask myself, what is this error? This error in this case would be the error in the appropriate norm for CD. And it turns out there is a theory that tells me, so what I've done in the past 2 years, I've developed a theory that tells me how fast, so is this thing going to 0? And how fast does it go to 0 as n goes to 0? I can say that this theory is very beautiful because I've not invented it. I've just lifted it from work that Atkinson has done in the 1980s, in which neural fields were not even on the map, but I just had to resurrect that work and put it in the context of neural field for time-dependent problems. But that's a beautiful theory that tells you that once you write things like that, there is a single writing for both the projections that you have seen, for both the interpolation projector and the Galerkin projector. So what Atkinson has done is worked out how to make this thing abstract so that both schemes can be written in this form. And by studying the theory of how U goes to UN, it catches both schemes in one go, let's say. And unsurprisingly, perhaps, not unsurprisingly, very surprisingly, actually, the error that you make depends on how well this approximation goes to U. So if you're asking yourself, what type of speed should I expect? This is the convergence of the solution to this problem. And what Atkinson manages to show is that it all depends on how un of x, this approximation, goes to a generic U. So there is a whole theory in numerical analysis that is the one that subtends finite element schemes, by the way. So we are now really tagging on their knowledge that tells you, oh, you want to approximate a continuous functions by a Galerkin projector or by an interpolation projector. Here is the rate of convergence. And now what we can do is we can take that rate of convergence, rate expressed in terms of n, so an order n cubed, an order n squared, and just plug it here. It is very hard for me to assess your appetite now, because you could be completely nauseous about what I just wrote and uninterested, in which case I have one suggestion. Or you might actually be curious about knowing how to prove statements like that, and I would have another suggestion. So my suggestion would be that depending on what you want to do in the next 30 minutes, I could either give you a glimpse of how this stuff is proved. You will not need this for this tutorial. Yeah, the tutorial goes on without knowing that. You know, I can tell you what to expect from the new app. The other opportunities that we'll leave this on the side, and perhaps in the next instance of this lecture, I'll give you a refresher of what I need for the stochastic case. And we now work more towards what you have to do in the tutorial, which is namely apply a collocation scheme, so the easy scheme, on a triangulated surface. So I give you a mesh that is actually a mesh of an hexagonal cortex or a mesh of a circular cortex that is split into tiny triangles. And these other opportunities to instead, I'm going to give you some elements of how you simulate this, literally how you form the matrices and how to practically implement that scheme. And we take for granted that there is a well-defined and beautiful theory about it, and we don't do any proof of that. First off, do you understand the options? Can I have by show of hands, just be open. I mean, I'm happy whichever way. By show of hands, who wants me to do a proof? I'm sorry, you are the minority. I was expecting that. Okay. So, this is not the last you see about projectors and schemes of this type. I'm gonna integrate this with some stochastics next time around. But let's look at something a bit more practical, shall we? So in the tutorial, I've set up everything that is required to reproduce the rotating wave that you've seen in the experiment. For those, do you remember at some point I showed you an experimental rotating wave on a hexagonal patch that was measured? And so I thought, why don't I take a neural field and I just I help you towards constructing that. In fact, I first want you to find out some form of spots, like the ones I showed you at the beginning of today, the ones that are kind of large dimensional with fast Fourier transforms, and then I bring them on a sphere, on a circle, and then on a hexagon. It looks a lot, but I assure you it isn't. So let's look at what is the equation that we're going to be dealing with in the tutorial. Am I running out of chalk? So we have this neural field. Now I'm going to switch to R because I want to remind myself that this is a three-dimensional neural field. And the cortex, the only assumption that I will make is that this cortex is now 3D. It's a surface in 3D, and it's triangulated. So let me just try to clarify for a second my assumption. My assumption is that the cortex, I can write it as the union of certain triangles. So what I'm writing is also written almost line for line in the tutorial of this afternoon. But I think I'm using hopefully the same notation. So the cortex that I'm envisioning is a cortex in 3D. Now, I don't know how much your imagination can stretch, but think that this is now some form of pyramid that you're seeing from the top. You are in R3. I'll remind myself of that through R3. I guess I'll need a bigger sketch, so let me make it bigger. These are meant to be triangles. Okay, so let's start putting some labels on them. What are our control points? We have 6 control points. In general, there will be n of them. So let's say that we have R1, R2, R3, R4, R5, and R6. And we name also triangles. It will be inevitable. TOE1, TOE2, TOE3, TOE4, TOE5. These triangles cover the cortex that we have, and they're done in such a way that TOE alpha interior intersected TOE beta interior is empty. So this is somewhat obvious from the drawing that I made, but it's important. So now let me make a statement that is that I'm offering to you just in case you are atrociously bored by this lecture. And it is in the tutorial. I mean, what it turns out is that to simulate this problem, you still need to solve a problem of this type. U prime of t equals minus u of t plus matrix f of u of t. And in the tutorial, if you want, you can just have the fun part of it, which means load M, load the mesh, and just start simulating the neural field. So there is a sense in which you can do the tutorial without forgetting everything that is stated and just lifting up the nodes and lifting up the matrix that goes with the nodes and just do that. But what I want to show you, because this is absolutely non-trivial, is how you can get M. And perhaps at the second pass of the tutorial, if you really are more keen, you can follow how I built M. And then I have a comment about sparsity. I owe you some. So how do we do that? Well, it turns out that everything hinges. Now I'm doing an implementation. So whenever I need to do an implementation, I cannot but invoke quadrature. So the trick that I told you earlier on, I want to catch errors higher up, is a pen and paper trick that lets me study errors. But once I want to implement it, I have to make an approximation of some sort. And it turns out that everything can be written in terms of a notable triangle, sigma. Sigma stands for the standard simplex in R2. But this is now not, so this one lives in R3. This one, it's made of triangles that are living on planes, so to speak. And this one now lives on just a flat, lives in R2. And it has vertices, row 1, row 2, row 3. And these are just the classical 1, 0, 0, 1, 0, 0. So in order for us to be able to implement collocation, we have to first rely on some form of quadrature rule. On sigma, not on the triangles, on the simplex. So if somebody gives me a function v on the simplex, I will use the coordinates rho. So this is now an integral over a subset of R2. I will approximate it using v at row, let's say L, no, row K, psi K, for K going 1, 2, 3. This is by far not the only option, but I'm now just giving you this one, that you only use the 3 nodes there. Quadrature rules that are in finite elements, they typically involves other points in the center of the, more in the middle of the triangle, but this is now the one important. What this means is that the moment I want to integrate over D a certain function, let me call it U of R dr, or R prime dr prime, what I'll do first, without approximation, I'm gonna split the integral over the triangles. I typically have M triangles. So this is carried out without any approximation. And then I will use a very astute fact about triangles, is that you can have bijections that send a 2D triangle to a 3D triangle. So there exists transformation, I'll call this transformation B to remind myself that this is a bijection. And I'll append an index 5 here and 4 here, to indicate that this is the mapping that takes the simplex sigma into a triangle T4, and this one is the one that takes it to the triangle T5. So when I do this, I can now say this one can be written like that. B alpha of sigma, U R prime, D R prime. Still, there is no approximation that has happened so far. I've just written down tau alpha as the image of this transformation. And this transformation does something quite nice. It says you can now, alpha, write down with a change of coordinates that problem as a problem with coordinates in the simplex. So what has happened now is that I have taken mu alpha to be the area of the triangle tau alpha. And what these bijections do is they work in such a way that you can ring the problem on the simplex triangle, the alpha, and what gets out is just the area. And now I'm in business because what I see here, it's nothing but a standard point, right? So what is this? This is now U at any of the nodes. So if I'm now asking what is going to happen here, this is now in the nodal coordinates. I can now apply the quadrature. So this is where the approximation comes in. I now have mu alpha here. I have a new sum that has to do with now, where is it? I'm now using this quadrature in which the function that I'm approximating is this. So I will now put k there. K goes 1, 2, 3. I have u at b alpha at selected rho k times psi k. So what has happened now is that if I want to approximate an integral over the cortex, all I have to do is get informations about the triangles, know each of the triangles area, and then know how to map from one to the other. So for instance, I would say when I'm in triangle 1, I'm gonna have to be able to see what is row 1 for triangle 1. Perhaps it's node R1. Then row 2 will be R2. And row 3 will be node 6 up there in the triangle. So what I'm trying to impart here is that everything that you see here can be computed from informations about nodes coordinates, from which you get the areas, and then connectivity matrices. So you need to be able to tell in that triangle which nodes are in that triangle. Now, let's just bring this all together before taking a break. That is, I want to now show you, so this is how you integrate UR prime in DR prime, but let's not forget, we have to do that on the top equation. Okay, so there is a nice twist that happens there. Give me a sec. Yes, I think I can introduce the twist here and then, yes, and then we move on. So this thing here, it's a little bit unmanageable by my taste. There is a way in which you can rewrite this thing that it's handy. So one way in which you can write down the approximation. Remember, we're approximating UR prime in DR prime, is to acknowledge that ultimately as alpha, so this is actually quite cute if you have not seen before. There is a double sum here, alpha and k. But ultimately, for any pair alpha k, I'm only ever ending up evaluating at a node. So what I'm saying is that however alpha and k are, alpha tells me a triangle, k tells me the ordering in that triangle. This one will be Rj for some Rj. So I'm getting ready to do something more simpler than that, which is to say, instead of taking these double sums, that is summing over the triangles and summing over the nodes, I want to recast this sum in such a way that the only thing that appears are the jth node. And this you can do if you just are careful doing some bookkeeping, which is never nice. I'll give you that. So in here, what I've done is I stated this lambda j is the set of all alphas and k's such that node, let me write it in words, node Rj is the k node in triangle alpha. So if you pre-compute these lambda j sets, then you can immediately pre-compute these weights, you call them delta j, and you have a very nice expression of this type, let's say. So let me just try to recap for a second. I'm telling you that in the tutorial, you will simulate that neural field. And the way you simulate that neural field is you will evaluate, well, the notes will have you that. You will evaluate u at Ri, and then you're going to have to take an integral over R prime. This integral, and this is shown in the tutorial, will end up being written like that, in which the matrix M is Wij delta j, with delta j written like that. So there is no difference. So if you yesterday have done the tutorial and simulated the problem in 1D, there's virtually no difference with simulating this problem on an actual cortex, except there is quite a bit of hairy work to do to keep track of all the triangles and all the lambda j's. In the tutorial, you can choose to just not do that, because I guide you through giving you a set of nodes. I give you a set of a matrix n that goes with these nodes, and I guide you towards visualizing that, and also towards simulating a neural field that produces a spiral wave. So you can even have a completely hands-on approach in the tutorial and forget about all this implementation of business. The only other comments I have to make is that the reason why this is exciting, to me at least, is because as of this year, which wasn't the case a year ago, we really are now in the business for coupling these problems with finite elements for PDEs. Because all of this technology that I'm now using here, it's not new. It's exactly the same technology that people use when they have to simulate finite elements on real. But when you see like a simulation of an F1 car or a wing of an airplane, that's exactly what they use underneath. They have to have triangulations or elements, they have to have connectivity matrices. And now we have both a theory that we haven't developed today that tells us what to expect in terms of convergence for a neural field. And also, let's face it, we have a technology because we can just tag on what they do to basically simulate proper neural fields. I am exhausted. Do you have questions before we call it a break?
One question.
Yes.
Is it the nodes? It's like it's imaginary, or each node should also be one neural name?
Okay, that's a very pertinent question. So I think the question you're asking is, do you, Daniele, view this thing as being the cortex is a continuum, and I am, well, or can I think of them as being just single neurons? And this is I don't know, it's almost a philosophical question. So yesterday, no, but it's actually, it's fair. Yesterday, you saw me write, you saw me, I don't know if you remember, there is a slide in which these equations appear 6 times. It appears as the equation of a single network of neurons, small network of neurons that are coupled. So I derived it as being neurons with the somewhat ridiculous assumption that these are rate neurons. They're not actual neurons. They are ones that we described from the rate. Then I say take the limit as neurons go to infinity, and I got to this equation, which is one variable, and I told you, oh, this is now a set of neurons averaged out. Then I took n populations of that, and I arrived at a connectomic version. The equation was always the same. This was just embarrassing. Play the video, you find it again. It was the same equation. And then I said, send the number of populations to infinity, and you get a neural field with the integral. Okay, so to some extent, if this makes you feel better, you can think of these as being neurons somewhere that you're discretizing. The way I like to think about it is that somebody has given me a prototype model. In this model, there is no neuron. There is a sheet of continuous neurons. This is a continuum now. Like in the same way somebody is giving me, when they write down the heat equation in a bar, the metallic bar, there is no notion of atom. There is just a position. And then between X and delta X, there are continuum mechanics, continuum thermodynamics ways of making sense of that. This is how I see this stuff. Somebody has given me an integral to discretize, and now I choose how to position these nodes and those triangles so that I meet some accuracy. The reason why I prefer slightly this view is that I'm getting ready to remove this neuronal, this rate equations altogether and to work with actual mean field problems of neurons that will not look like this, and in which I'm going to be giving a tissue and then discretize it. But I am biased, and who am I kidding? These are just also equations of neurons, if you believe the rate equation. Sorry, perhaps that was long-winded. Any more questions?
What will be one use of this type of simulation?
One use of this type of simulation? So at the moment, were you there when I showed the rotating, the spinning brain? Let me just show it again, just because. So we are now at a stage where somebody can give me a piece of cortex. And in this particular simulation, what you see is that in the prefrontal cortex, there is an abnormal oscillation, so to speak. And not only in here, the grid points are picked up from human data, but also the who connects to whom. So this one is it's something that we call synaptic connections that try to model how many wires there are in between 2 points in the brain. This is very far-fetched to say, but this is a measure of synaptic strength in between two things. And what I'm literally trying to address is simulating these as an organ. So yesterday we saw experiments in which patterns were observed of, let's say, waves in epileptic seizures, or we saw at some point spots that are formed in your visual cortex. So there is a part of the brain that has to do with how you transduce signals from the visual domain. And they all form patterns, so we're getting ready to simulate that. And I think to some extent, the exciting part for me is that we can now start treating these as an organ. So as people come up with new models, they will certainly have that W structure there for sure. They'll be more complicated than this. They'll have multiple population of neurons. They'll have nonlinearities elsewhere, but we're now ready to just do that. So if you ask me what I am trying to do at the moment, is I'm trying to simulate these things, having uncertainties in the forcing. So there is an application that is called transcranial magnetic stimulation, in which patients that have severe depressive disorders are treated with very strong impinging magnetic stimuli in the prefrontal cortex, in the hope that some limbic structure, so underneath the cortex, gets stimulated. And what we are getting as evidence is that is whether this treatment works or not really depends on the patient. So it is non-invasive, so people just go out like they're drinking water, basically. There is no side effect, as opposed to other medical treatment for people that have this type of disease. And however, half of them is literally just drinking water, nothing happens. And so the belief now is that this has to do with what is their wiring structure to start with. So what I'm now excited about is that I can try to make models in which I say, oh, there is uncertainty in that W, I simulate many scenarios, and then I try to give people statistics. But that's more an announcement of what I want to do rather than what I've done so far in the field.
So there's a possibility that you can also use this model for invasive type of.
Yeah, that's, I mean, whatever you want to do in terms of whether invasive or not, let's say you will have to write down some form of equation for neuronal activity. And it seems to me that all your model, they will not be like that, but they will have similar features. You'll have to deal with this integral one way or another. And I haven't talked about sparsity, but I think I can tell later, let's say. Shall we call? Yes. I mean, yes, go ahead.
Yeah, but the example you just talked about, I'm just curious, for the people, what you said, half the people doesn't do anything for, but half the people does something for.
Yes.
What does it, like, does it actually, like, help, how does it actually help them, just out of
Okay.
curiosity?
So if you read literature on I would say psychiatrists that impart magnetic stimulation with patients, there are two types of measurements that they do. One is a measurement of activity. So there is a, let's say, there is growing evidence that activities in certain areas of the limbic brain, so areas that are non-cortical brains, is correlated with, depression or lack thereof. This is a very vague statement to me, but let's say, so one thing that people do is that they measure activity or correlation of activity in different parts of the brain before and after the stimulation. They find out, oh, that there is an increase in activity, and that hopes to just relieve a patient. However, most kind of evidence is literally not in the form of a measurement or like a quantitative measurement, but more like a qualitative measurement. How do you feel after a month? Do you feel any benefit from that? So it may even be placebo, but it doesn't seem like the case. It seems that some people that get TMS, this is now getting it's currently imparted in patients. Some people literally get benefits out of it, and they are typically in the form of they feel better.
Okay,
And they need a return. Sometimes they need a recurring. What I hear is that they need a new session after some time. But the general belief is that increases in activity in certain areas of the brain is correlated with also abnormal feelings, if I can call them like that. I'm not really. You will have noticed. I mean, I have difficulties in talking about this because I don't know much myself.
So you use that if you, for instance, if you think about the invasive implants like Neuralink, you could use this somehow measurement of brain.
Don't go tell them, because otherwise they will do it. Exactly. I think they are already doing. I don't know what they do, but certainly they would have evolution equations. If they care about evolution equations, they would be in this form. But the main reason why they should be, I think, one way or another, you end up in these forms because this is also our artificial intelligence. So already people, perhaps steady states version, but artificial neural networks are already written in that way. So I don't know what they do exactly, but I'd be surprised if they don't have this technology in many ways. They may do that without caring about convergence, though. Yeah.